thank you for letting me know. I was muted on my end. So yeah, so to say again, I've gotten first drafts from nearly everyone, and so we should be. I'll try to get comments back to everybody by tonight. My time. So and if I don't, then worst case scenario, I'll just push the deadline back one day. But are there any questions before we get started, either about final projects, the presentations, anything else? All right. So we're going to talk more about partial differential equations today. You can submit it this weekend. I have to get everything graded out and done by, I think, Wednesday. So I am gonna have to make that cutoff for that probably Saturday, just to make sure. But yeah, any other questions? Yeah. So as you can see, I'm back on the quarantine porch. So this has been a tour of interesting places to teach classes from. I hope it hasn't been too much of a pain for you guys. But yeah, so today we're going to talk about modeling with partial differential equations. Modeling with So last week on Monday we looked at one example. So actually we've kind of looked at two examples. So the example of the heat equation, and how do we then use the heat equation to talk about things like homogeneous boundary conditions? How do we actually use it in situation when we have something like a day-night cycle and a heating column? And then we talked about the fact that the heat equation is actually equivalent to the Brownian motion equation, right? So that if we have a system where we have small particles that are making discrete jumps with some probability, that we actually expect that when we zoom out, when we take the statistical mechanics picture and we really look at the tiny little particles and we zoom way out, that the bulk phenomena. Oh, thank you. Luckily, I haven't written anything yet. I'm just pontificating, but thank you very much. This is clearly the closer that we get to the end of the semester, I swear, the more my brain goes. And so now that we're at the last class, my volume's not on and I'm not sharing my screen and whatnot. So please do yell at me when I do something. So last time we saw the Brownian motion. So these are, anytime you have phenomena that can be sort of cashed out as discrete jumps. So a bunch of particles making discrete jumps in space. It turns out the equation that you get out of that is the same as the heat equation, which again was this kind of shocking theoretical justification for atomization, right? There were people that believed in atomization, there were people that didn't believe in atomization. There was a lot of evidence for it by the end of the 1800s, but the fact that you could reproduce high-level heat flow phenomena from low-level kinetic phenomena was really quite shocking. And it follows in the theme of everything that we've been doing in this class so far. I mean, in some sense, this really is a mathematical modeling with differential equations and atomization class, right? We take discrete small populations and we assign them very, very simple behaviors, whether it's the SIR model or the, the radioactive decay models or the population models. And then we see what happens as we zoom way out and try to look at bulk density phenomena. And the last thing that we're going to cover is looking at one final example of that, which is a historically very important example in mathematical modeling. It actually, and that's traffic flow modeling. So traffic flow modeling is the beginning of smart cities modeling. It's we've all been in a situation where we've sat in traffic. This is like the stupidest way that they could have possibly put these stoplights. How would I figure out how to do it better? And one of the goals of this traffic flow modeling is to derive some basic rules of how phenomena that we see in populations and crowds and movement and traffic work. So we all know that there are things that happen, like phenomena of somebody puts their brakes on, and somebody puts their brakes on, and then an hour later there's huge traffic jam. What speed does that traffic jam backward? Where can we model this phenomenon? Can we come up with some rules for it? How do we understand the density change in traffic when things happen, like stoplights turn on and off? And how long does it take for this phenomena to catch up to each other? So we're gonna derive a couple of quick rules for that today, and we're gonna show, in particular, we're gonna show how to derive more rules. So my voice is breaking. Okay, thank you for letting me know. Is it breaking like bad internet connection breaking, or is it breaking like my microphone is not working breaking? Okay. I have another mic I can use. Now it's clear. I put the tablet on top of my laptop, so I wonder if that's it. Okay. Thank you for letting me know. And please do let me know if that happens again, because I do have headphones that I can use if I need to. Okay, so our goal is to get to traffic modeling with PDEs, and our route there is going to be going through what's quite a general method for getting solutions to partial differential equations. And then that's called the method of characteristics. So has anyone here taken a PDEs class before? Okay, so it sounds like no. So that means that everyone here is going to be kind of on the same page. So I want to really encourage you to ask questions. I will try to go slow and be as clear as possible, but it's a difficult subject, and we will get some good results without too much work. But I would very much encourage you to ask questions if you have them. Okay. This isn't really, so we'll do a first example. So this isn't really a first example. I shouldn't say that. But this is the first example in the world of characteristics, which is what we're going to do. Okay, so back to our pollution modeling. So let's say that we have the following situation. So we've got a lake or a river. We've got water in it entering one end and water leaving at the other end. So, water so water is going to enter at x0 and leave at xl. Okay, so if the water has, so we're interested here, so this is going to be pollution in a lake. So in this case, the water is going to have some concentration of pollution that's going to be a function of both x and t. So concentration of pollution C of t. And we're going to make a final assumption, which is that there's a nice constant flow rate. Okay, so kind of picture here, right, is that we have water flowing through at rate F. And so what we want to do is we want to play our differential equations game now. So we want to write some equations. So if the water is flowing at rate F, we want to write some differential equations for the concentration and figure out, we'll then specify some initial conditions in a little bit, but we want to figure out how we expect the movement to go. So in this case, this is like really, really simple, right? Like if we think about it for a second, we just have a constant flow rate. So if I have some initial, concentration in the lake, what would we expect to happen to that? Just without doing any math, just kind of purely intellectually. So what would we expect to happen if we had like, so if we have a constant flow rate and I've got some pollution enters here, say, what do we expect that pollution to do in just the simplest model where we're not going to like try to do diffusion or anything like that? We just have a constant sort of flow rate through the system. It'll get contaminated, but how do we expect this to sort of update through time? Or how could we expect it to update through time? Well, there's like a couple of things that we could expect to happen, right? Yeah, so one thing that we could expect to happen is kind of what Annalie is saying, that we could actually expect it to diffuse out, right? And this would we would expect to actually follow the Brownian motion equations, where if you put it in a large volume of water, it'll kind of diffuse out away from this. And eventually the concentration will go down to some constant probably. We're also, though, in the flow example, since we kind of know how to deal with diffusion, in the flow example, we would sort of expect it to just move forward, right? So if this is at time t equals 0, then at time t equals 1, we might be down here. Actually, at time t equals 1. And this difference here, right? So this difference is exactly going to be F in meters per second. Or sorry, F times A. So if we're flowing, the example being, if we're flowing, if the water is flowing at 10 meters per second, right? And we've gone 1 second, then we would imagine that the concentration will have moved on 10 meters as an example. Okay. So we could include as sort of a first thing, so this is actually going to be a sort of really stereotypical example of a wave solution, right? Where we're going to wind up with is something that's kind of symmetric in space and time. So as we move time forward, all that kind of happens is we just sort of push the concentration function along in space. The concentration, if we don't include something like convection, then all that happens is that the original density just moves downstream without doing anything else. So let's try to model that really fast. So the idea here, just look at, we have some area. So x and x plus delta x. And let's fix delta t. And then we can get delta x by the flow rate. So in 1 unit of time, whatever our delta t is, we'll think that everything in here has flowed forwards 1 unit. So it has exactly gone and replaced. This is going to be x plus 2 delta x there. So everything that's between x and delta x has then moved on exactly to the next sort of portion of the river. Okay, so then our equations, right? So we want to write down a word equation or kind of think about it. How is this flow going to work? Well, the thing that we have here is conservation of mass, right? We know that the masses are supposed to be the same. So that means that the change in mass is going to be the mass in minus the mass out. The mass coming in at x minus the mass going out at x plus delta x. And of course, the conservation is just related, sorry, the concentration is just related to the mass by multiplying by the volume, right? So the actual equation we're going to write down, so here, mass in is just equal to, well, the concentration, and we're going to approximate it here. So actually, I should say it should be approximated by the concentration at x at time t, right? Oh, sorry, the mass coming in. So we'll center ourselves at x. So then the mass coming in is going to roughly be the concentration one spatial step back, x minus delta x times t, then plus the cross-sectional area, times the cross-sectional area, times the width, right? So the volume, so this is just here the volume of the section of the lake. And this is roughly the concentration in that lake section. Okay. Okay, great. But so then by this observation here, we can rewrite this as, so delta x is just the flow times the time, right? So how long is delta x? Well, we said it's 1 unit of time times the flow. Great. So A delta t times F. Okay, so this is gonna be our mass in. Our mass out is gonna be almost exactly the same. So then as an equation, so the change in mass is going to be this. So then what is the change in mass? Well, it's going to be the mass at time t plus delta t minus the mass at time t. So it's going to be mass at t plus delta t minus the mass at t, right? Great, change in mass. And this is going to be equal to, well, it's just going to be, again, the volume times the concentration at those times. A delta x times c at x t plus delta t minus c of xt, where again, this is an approximation that will get better as delta t and delta x get smaller. And then this is supposed to be equal to the mass in at x and the mass minus the mass out at x plus delta x, which is, again, A delta t times F times C x minus delta x, the mass in minus the mass out so minus the mass flow out, right? So how much are we losing each time? Well, we're losing the amount in is moving on. So, and again, this is just in a sort of a big chunk way, right? Everything in there, the entire concentration, since the flow is constant, just moves down. And the new volume is the entire concentration from the previous sort of slice of the river moves in. Okay. And so the nice thing about this, right, is that we have delta x on the left-hand side, delta t on the right-hand side. We've got a shift in delta t and we've got a shift in delta x. So dividing both sides by a delta x delta t, we get c of x t plus delta t minus c of xt divided by delta t. It's going to be equal to oh, sorry. I don't want an A there because it's going to be F over A times C of X delta X T. For delta X and taking the limit as both sides go to 0, we get A partial differential equation, something actually relating the space and the time variables. Okay, great. Yeah. All right, so what is this? So again, whenever somebody presents you with a partial differential equation, you should think about, so what kind of thing is this? Well, it's first order, good. We're only looking at the first derivatives. And it's homogeneous. So this is genius. And actually, I think that I don't want, sorry. I think that I just want the flow there. There's a disagreement. So this is, again, where the book has a little disagreement with what I think is correct. And I think that I gave you guys the correct version. And the book has an issue here. I think we just want the flow. Yeah. Because if the flow is in meters per second, then the units here work out. Okay. So this is the first order homogeneous. And with that, we can write it partial C partial T plus F partial C partial X equals 0. Okay, any questions? All right, so we can actually, I would encourage you to say, so I would say we can actually solve this in a very straightforward manner by realizing that it's a wave equation. So not a wave equation, by trying a wave solution, right? So if we try a wave solution just like we did for the moving gene, for the gene diffusion model, and I would encourage you to try this. So find a solution by guessing that it's a wave solution. C of xt is actually C of x minus vt. Okay, so I'd encourage you to give that a try. We want, though, to look at a much more general method here. So basically, getting away as much as possible from the guessing and checking. What general methods do we have to solve PDEs? So I would point out this is a general method. It is not necessarily the best one. It is not necessarily the correct one. It's certainly not the only one. But it's one that gives that puts us a little bit more on the actual spatial setting rather than sort of guessing a solution and checking. And of course, the other thing that we did, right, was we did the separation of variables, which again is fine, but we are kind of making pretty strong assumptions about what the solutions to the PDEs could possibly look like, right? They have to be just multiples of a function of t and a function of phi. And you can get quite far with that, it turns out. But we want to do something that's like inherently spatial, something that inherently sees the PD, so the time and space variables as two-dimensional, as a sort of two-dimensional set of equations, or a two-dimensional equation. So this is known as the method of characteristics. And I'm going to demonstrate it instead of writing down a theorem. I'm going to show you how it works first. So in this case, the method of characteristics revolves where you have to have fixed boundary conditions. So fix the following boundary conditions. We're going to fix the following boundary conditions. So there is some initial pollution profile for the lake. That is that C of x at time 0 is just given by some function p of x. Great, so there's just some initial concentration. And then we have pollution entering from the left-hand side. So we've got pollution entering at x equals 0 as C of 0 t equals f. Okay. So we've got some function for the initial concentration, and we've got some function for how things are entering, right? And if we kind of have a picture here, it would be if we've got our x and we've got our t, right? Then we've got some initial sort of functional profile. Whatever it happens to be. P of x. And then as we start running time forward, we'll have some new rate at which pollution is entering. Oh, sorry. G of t over f. So we've got some rate at which pollution is entering. And then the question is what happens in the bulk? So what happens at xt, or what is the concentration? Okay, so quick question. So given that the only thing that we're modeling is basically just the pollution just moves down the river, does anyone have sort of any idea of like what we should expect the solution to look like? Like if I were to ask you, so given this, like given like what I've drawn here, this sort of picture, what would the solution look like at a certain time? Or sorry, not what would the concentration look like at position X at time t, where X and T are non-zero? So I would say the sort of the picture that we should maybe have in our heads here is that so we've got some initial pollution profile which will flow on down the river completely unchanging, right? Because we haven't added any diffusion terms or anything like that. And then eventually we'll have some new pollution coming in. So for the first, for some period of time, you just basically look back at the, so how far out down the river are you and at what time? And the first thing that will happen is the entire initial pollution profile will pass by. And then the function g of t over f will start passing by in front of you as well. So let's see that. But first, are there any questions before we jump into the actual method of characteristics in solving this equation? Yeah, so the reason, so P is just, exactly. So P is just some random function. I mean, positive, it's concentration function, so it's a random non-negative function. But it is giving exactly as you say. So it's giving an initial profile at t equals 0, right? So it's basically saying, so right now, when we start running this differential equation forward, what is the initial concentration? Does that make sense, or? And so that's also, that's why it's only a function of x for a single fixed time. Okay, so the idea behind the method of characteristics is that we want to find, instead of like solving for the entire space, we want to find lines and curves in the solution space. So we want, to find curves in the domain where the PDE reduces to an ODE. So what we're going to do is we're going to say let x of s, t of s, it's gamma of s, be a curve in the domain. So be a curve in the xt plane. And then we want to try to write a new differential equation. We want to write, so dds of c of xt is equal to, well, okay, by the chain rule, this is going to be dc dx, so sorry, dx ds plus dc dt dt ds, and we want to write this as, so we want to write this, the PDE above, we want to turn it into an ODE along this line. And so in order for that to happen, we want it to be the case that this actually matches up with our ODE above. So this is going to be dc dx times f plus dc dt. And again, the reason for this is that we can solve, is that basically we know how to solve ODEs. And this is equal to 0. So if you see what we've done here is now we have a system of ODEs. So a system of ODEs, so the first one is dc ds equals 0, right? So just using, so this is a homogeneous ordinary, sorry, a homogeneous PDE. So we're gonna have dc ds equals 0. And then we want these guys to match up, right? Formally, there's a 1 here, right? Write these in a different color here. And that's going to give us 2 more ODEs. So in particular, dx ds needs to be equal to f, and dt ds needs to be equal to 1. Okay, so kind of the picture here, a side picture. So the aside picture here, right, is that what is C? Well, C is some function, right? So we have our x and we have our t, and we have some function C, right? So this is C of xt. So instead of trying to find this function explicitly in terms of xt, we can look downstairs and say, well, can we find some interesting curves that make this, that match up the differential equation? So in this case, dc/ds actually is going to tell us that downstairs we're looking for curves such that the rate of change of the function is actually constant. So we're actually looking for the, I think it's the isoclines is technically what they're called, but we're looking for the curves of constant value downstairs. And on those curves, then we can solve this function. So the dx ds dt ds is going to give us the equation for the curve itself. dx ds t ds give the equations of the curve, and then dc ds is going to give the equation of dc ds plus the boundary conditions. Gives the value of c along the curve. So here, this is gamma of s. So basically, what we're going to do, what hopefully we'll get here, is a huge family of curves, right? Because we know that when we solve systems of differential equations, systems of ODEs, we tend to get families. We actually tend to get what is called a foliation of space, right? So where we sort of have this cutting up of space into an infinite number of parameterized submanifolds, kind of leaves of space. And then on each one, we'll have a simple ODE, which hopefully we can solve. In this case, it's a really simple ODE, right? It's just the function's constant. That might not always be the case. So it could, of course, be that our original equation wasn't homogeneous. So it could be that this right-hand side here isn't 0, but it's something else. In that case, then this would be a non-trivial ODE. But okay, so that's the plan. We're going to try to solve these two, the ODEs in terms of x and t for some curves. And then we're going to use the ODE in terms of c to find the value and the boundary conditions to find the value along those curves. Any questions? All right, let's do it. Find curves. Okay, so in this case, what? dt ds equals 1. Dx ds equals f is pretty straightforward to solve. So integrating both sides, we're just going to get that t equals s plus t naught, x equals f times s plus x naught. Great, so hopefully that's straightforward. So the nice thing about this, though, so this, of course, gives a parameterized curve. So if we want the equation form, what do we get? Well, setting both sides, equating s, we're going to get t minus t naught is equal to x minus x naught over f. Okay. So what this is telling us is that we actually have straight lines. So these are called the characteristic curves. Let's say. straight lines. And so back to our picture here, with our x and our t, and we have some boundary condition at x equals 0 and some boundary condition when t equals 0. This is what the characteristic curves look like. Okay, and so we can actually see exactly what I was saying before, right? If the water is just moving, what do we expect if we're standing somewhere downriver, right? So let's say we're standing somewhere downriver at x equals L, for instance. So the first thing that happens is we see all of the, so as time moves forward from here, so the first thing that happens is we see the initial profile go sliding past us, right? That's what we'll see up here as we pass through here. You know, what is it at this time? Well, since the ODE is constant, right? So since along these curves, we have that DC is equal to 0, we'll just get the value of P at X naught at this point, right? We'll get the value of P at this point. Here we'll get the value of P at this point. Here we'll get the value of P at this point. And then eventually we'll go back to, you know, so we'll get to the initial profile at X equals 0, and then we'll start getting the value of the function g as it flows into the river at time t. So I'll actually do that mathematically, but does that sort of make intellectual sense, or are there any questions about that? Okay, so here are the characteristic curves. So along the curve gamma, so again, this is t minus t naught equals x minus f over f. The following differential equation holds. dc ds equals 0 holds. So, however, we also know that, so since t equals s plus some constant, so that the only difference between s and t is sort of linear shift, it also holds that dc dt has got to be equal to 0. I'm sort of, well, actually, I don't even need that. Yeah, no, I don't need that. Maybe. We can just say it directly out of here. So since S parameterizes the characteristic, the fact that this holds means that C is constant. And so is determined by its boundary condition. Okay, so I just want to point something out here. It's very clear, right, that maybe it's very clear that we could accidentally write down completely contradictory boundary conditions, right? We easily write impossible boundary conditions. So how? Can you think of an example? So remember, we've got two boundary conditions. What have we said? We've got two boundary conditions. We've got one here. So this is P of X. We've got one here. This is G of T over F. We've just gone through and said, so in this differential equation, using this method of characteristics, how do we figure out what the value is? Well, it's constant along a curve. So basically what we do is we just what we're going to do, we're going to, for any point, we're just going to backtrack along the characteristic curve until we hit a boundary condition, and that's going to be the value. So how could we write down contradictory boundary conditions, or boundary conditions where there was no solution? What would be an example of such a boundary condition? And if you can't think of one immediately, just remember that boundary conditions are really general, right? Like I specified these boundary conditions that make sense. They don't have to make sense, right? They're just things that we're specifying initially. So here's one way we could do it, or the other way. So we can easily write down boundary conditions that can't be satisfied. And the reason is that what this has told us, right, is that C is constant along the characteristics. So if one of the characteristics intersected two boundary conditions, we could easily have an issue. So if a characteristic intersects two boundary conditions with different values, we can't solve it, right? So for instance, let's say that I'd specified, oh yeah, so it's going to be a certain value coming in here, and then it's going to be a different value going out here, right? Then you've got the problem that it's supposed to be constant. So the characteristic is supposed, or the value of C is supposed to be constant along this characteristic. But I might say that it's 4 here and 5 here. So that's clearly not going to hold. And so that's the important thing to remember, is that it's entirely possible with partial differential equations. Like with ODEs, we kind of had this thing where it was like, whatever we specify for X naught for the initial conditions is just some linear system and we can always solve it. That is not going to be the case with PDEs. It's actually quite easy to write down boundary conditions you just can't solve. Any questions? Okay, so let's actually go through then and solve this. So let's say, okay, first, let's assume that the characteristic intersects the first boundary condition. So intersects the P of X boundary condition. At X not 0. So what does that mean? So let's say that we have some point here. We have some point xt. So for a point xt, the characteristic passing through xt is going to intersect the boundary. Boundary. At, well, so we've got t equals x minus x naught over f. So that implies, so here I can set the t naught equal to 0 because I only need one of these. So this is going to imply that x0 equals x minus ft. So that means that, so along this line, right, if we go out on this line out to that point, so if I have a point xt and I trace backwards, where is it going to hit the x-axis? So the characteristic passing through xt hits the x-axis at x naught equals f minus, so x minus ft. So the value of c is c of xt is equal to p of x minus ft. And this is going to hold provided that we actually hit this boundary condition here, right? There's going to be some bright dividing line between our boundary conditions. But as long as the boundary condition that we hit is this one, so as long as we're down here, right? So we hit the initial profile, so we hit the the t equals 0 boundary condition. Then the concentration is just going to be given by P of x minus ft. And what is this line, right? This line here is just the line with this slope that passes through the origin. So this is just t equals x over f. So this is t equals x over f, t equals 0. This is going to be x over f is greater than t. Okay, so let's run the argument the other way. So second, when x over f is actually less than t, then where are we? So then we're up here. Then we're up here, and the boundary condition that we hit is the boundary condition of the inflow, right? But otherwise, the same thing happens, right? So when x over f is less than, boundary condition comes from the inflow. Characteristic intersects the boundary condition at x equals 0. Okay, and so we need to just go back and figure that out. And so again, if we're here, so if we are at the, so if we're at x of t, so for, again, we can rewrite this equation. So setting the x naught equal to 0, since we know that we're passing through the x-axis, we only need to keep x or t naught. So for t minus t naught equals x over f, we just need to figure out what t naught is. So t naught is going to be where we intersect the t-axis, and this is going to be so t naught is going to be at x over f minus t. So this is where we actually intersect the axis. And so along the characteristic, g of xt is going to be equal to g of x over f minus t. Oh, sorry. I've got this the other opposite way around. This is going to be t minus x over f for t greater than x over f. Yes, thank you very much. Okay, and so now putting them together, we've got our solution. And that is that c of x t is going to be equal to, well, p of x minus f t for t less than x over f, and g over t minus x over f for t greater than x over f. Okay. So this is the method of characteristics. And I want to pause now and just make sure that we understand it, right? So morally, kind of intellectually, what's going on is that we're finding characteristic lines. So we're finding we're taking our PDE, we're writing it again as a sequence of ODEs along specific curves in space. And what we wind up with out of that is some curves in space where we can solve the ODE, and then so we can solve an ODE giving us the actual curves, and then we can solve another ODE along those curves, which gives the value along those curves. Mathematically, it's actually pretty straightforward, but like sort of intellectually, it's well, I should say computationally, it's pretty straightforward. We have pretty much done all of the ODE solving that we know that we can do. The only sort of complication is figuring out where we hit the boundary conditions. But it can be a little bit to get your head around. So I just want to, are there any questions about how this works? Okay. All right, so let's get to the meat of today's lecture. Well, do you want to see one more example of the method characteristics, or should we get on to the traffic modeling? We will use the method of characteristics in traffic modeling. This won't be the last time we see it. Okay, well, I'll jump onto the traffic modeling then. But the idea here again, so just the solidified idea that I want you to have in your head is we're finding lines where we can solve, so instead of solving the ODE on the entire bulk, we're finding certain lines where we can solve it, and then certain curves. So in general, these can be general curves. They can do all kinds of crazy stuff. And then from there, we solve the one-dimensional equation along the curve. Okay, so traffic. Density and flow. Okay, so what's the picture here? So we want to model traffic along a one-dimensional road. Model traffic along one-dimensional road. So an immediate extension of this model would be doing it along like a freeway where we actually had, say, two one-dimensional roads. We had some rules to transfer between the lanes. But the picture here, of course, is that we're just going to have X. And what we want to do in this case is we actually want to measure the density. We want to model the density row, not the individual cars. We'll look at an example at the very end of modeling the individual cars. So you can kind of do that as a system of ODEs. But so we want to model the density, not the individual cars. And so here, this is basically going to be, could that imagine that we have some density and then it gets denser and then it trails off, right? So this is the density at a certain time. And just as a reminder, with density calculations, so even if the density is constant, we could still have traffic flowing, right? So this is just, it's like, this is exactly the same as the heat, right? So we could have the temperature be constant, we could still have heat flowing through the system. It's just that we have the same amount of heat coming out one end as we have going into the other end. Okay, so this is roughly going to be our picture. And so we want to, usually, I mean, in some sense, all the equations that we have are about constraining the possible space of functions down to some interesting subspace, right? And so mathematics, usually what we want to do is we want to think of everything in terms of constraints. And in physics, of course, your constraints are your conservation laws, you know, and these are the things that give rise to all of the interesting physics that we see, is that only certain functions satisfy certain conservation laws. In this case, the conservation law that we're going to use is a pretty straightforward one. It's just mass conservation, or in this case, it's conservation of cars. Conservation of cars. Oh, sorry. There's a big assumption that we're going to make that I want to maybe just state up front, because this is like not an uncontroversial assumption, but I think you'll agree it makes sense. We're going to assume that the traffic speed depends on the individual car speed depends on traffic density. Okay, so this is obviously like true in some sort of sense. Like, you know, if there's nobody on the road, then you just go the speed limit. Whereas if there's tons and tons of people on the road, then maybe you will slow down. But of course, that's only true in like a heuristic sense. You know, you can be on an incredibly crowded highway and everyone's going 60 miles an hour. It's just that there's in general, you know, highly dense traffic is correlated with an increased with a decreased speed. Okay, conservation of cars. So let's fix a section of roadway. A, fix a section of road. So thus this will of course be a closed interval from A to B. The number of cars, or so it should say, a section of road with no entrances or exits. So then the number of cars is just going to be the integral of the density of cars. The integral from A to B of the density of cars at time t. And in particular, I should say n is going to depend on t. So the number of cars in a section is the integral of the density. Hopefully that should be relatively uncontroversial. So again, if the density is, you know, number of cars per unit, you know, per square meter, something like that, or per, you know, per unit length, then the total number of cars across the entire interval is just going to be the integral of that. Okay. So, sorry, I should pause. Are there any questions before moving on? Got a 1D flow. We're looking at density. We can get the number of cars out. Of course, we're looking at density because we want to look at something continuous. Because this is not a class about Markov models or agent-based modeling. So we've got some cars. So we can get, so given the density, we can get the number of cars out. Of course, n might change with time. And the sort of the word equation we want to come down with is word equation is going to roughly be the rate of change of the number of cars is going to be the number of cars entering the interval minus the number of cars exiting, right? Well, I don't know. This satisfies a conservation equation. And that is that the number of cars within the section of u in time is the number of cars entering. Yeah. So let me say it this way because I'm going to write it down slightly differently. Rate of change of n is the number of cars entering at A minus the number of cars exiting I should say per unit time exiting at B per unit time. So this is assuming that there's no spontaneous creation or destruction of cars, right? So any car that comes into the system needs to enter at A, and any car that leaves the system needs to enter at B, and there's no other mechanism by which cars are created or destroyed. So we're going to let Q of X T be the traffic flow that is cars per unit time at X at time T. Okay, so the velocity, going to get similarly, so the velocity v of xt, which is going to be, length per time, is going to satisfy the equation satisfies that the traffic flow is the velocity times the density. So this equation really follows from, if you just think about the discrete case, right? So like the discrete case with the constant case. So if we've got 100 cars per kilometer, yeah, so if 100 cars per kilometer go 50 kilometers per hour, then how many cars do we expect to pass in an hour? So just as an open question. So if you're standing there on the side of the street and the density of cars is uniform, it's 100 cars, it's 100 cars per kilometer, and each car is going 50 kilometers per hour, how many cars do you expect to pass by you in 1 hour? I feel like this, people either think that this is trivial or are confused. So if you think this is trivial, just type the answer in. Otherwise, I will continue to explain this because I don't know. I like this. This is like a little the functional version of this was a little counterintuitive to me. The units check out, but it wasn't entirely clear. So you've got the right idea, but you're going the wrong way, right? Draw a picture, right? So if we have one, two, three, four, five, six, seven, 8. So this is 8 cars per kilometer. 1, 2, 3, 4, 5. Oops. Eight cars per kilometer. And so if they're going 2 kilometers, these guys are going 2 kilometers per hour, then in an hour, we would expect all 16 cars to pass by me, right? Or I guess I can just do it with the units. I like it. So if we have 8 cars per kilometer, in an hour, all of the cars they're going 2 kilometers per hour, so per hour. Then in 1 hour, all of the cars from up to 2 kilometers away will pass by me, right? So since there's 8 cars per kilometer, in 1 hour should have 16 equals 8 times 2 cars pass by. So does that make sense? So that if I have So if I'm standing there and I'm watching cars pass me with a velocity v with density rho, that the number of cars that pass per unit time is going to be v times rho, is what we're seeing here. And so in this case, the answer here is going to be 100 cars per kilometer times 50 kilometers equals whatever that is. 5,000 cars. It's totally fine. Like I said, I mean, I wanted to pound on this a little bit because I actually found this kind of counterintuitive. Now, I'm not. It's a density calculation, which seems to be like pretty straightforward, but I did want to make sure everyone understands. So, are there any questions about this at this point? Because this is going to be the key relationship through the rest of this discussion. Okay. So there's a couple of different ways that people get from this setup to the differential equations. I'm just going to show you one. So let's write the traffic flow difference. So Q of A T minus Q of B T. So the difference in traffic flow at either end. Right. So again, since we have this conservation of cars, we should be able to say what the total density is, what the number inside is, by just looking at the traffic flows at each end and comparing them. On the other hand, of course, this difference is just given by like a silly integral identity, right? We could write this difference as the integral of ddx of q xt dx, just by the fundamental theorem of calculus, right? Anytime you get a difference like this and you're trying to construct some sort of differential or integral equations, this is something you can look at. And then, so what do we have? So the conservation equation is going to become the following. Sorry. Conservation then becomes, right? So the conservation equation, right, was the rate of change in n. So the number of cars entering minus the number of cars exiting, right? So that's going to be, so the rate of change of n, d dt. So what is n? Well, n is the integral from A to B, rho of xt dt, is the number of cars entering, number of cars exiting, is equal to minus the integral from A to B, del del x, u of xt. This again. N. But luckily we have an integral with the same, oh, sorry, this should not be dx. N is the integral of the density across the entire region. Okay, so luckily we have, these guys are both under the same integral sign. So we can rewrite this as, and so we can swap integrals and derivatives. So we have that the integral from A to B of d dt of rho of x minus d dx of q. Dx is supposed to be equal to 0. Okay. But we have this fundamental relationship between q and the velocity and rho, right? Q is equal to v times rho. And so this is where our big assumption comes in, right? So let's say that we can write the velocity as a function of rho. So if velocity is a function of density, i.e. v of rho, sorry, v equals v of rho, then we actually get an honest-to-God differential equation out, right? So then ddx of q is going to be, oh, sorry, then I should say, so then q of xt is equal to rho times v of rho. So if we define C of rho as u prime of rho, and we could write the conservation equation. And so what is it? It's going to be d rho dt. This should be plus, I apologize. D rho dt is equal to C of rho times, sorry, partial rho, partial x equals 0. Okay, so again, what have we done? So we're trying to get to the place of actually having a partial differential equation. That can be a little vexed, or a little tricky anyway, because we've got, because, well, we're doing things in terms of density, the conservation equation that we get directly is still in terms of two functions, right? If we assume that the velocity is independent of the density, then, well, I mean, there's stuff we can say, but really, it's we pretty much just have a differential equation in terms of two functions, which is there's just not a lot in that we can say in terms of definite solutions. So we have to make an additional assumption. We have to somehow relate the density and q. And a simple way to do it is just to say that the velocity is dependent on density. Now, of course, as we said, this is kind of a bad assumption because, of course, it is not true in general. You know, you can have everybody speeding along bumper to bumper at 60 miles an hour. But in general, we know that that doesn't, well, that happens sometimes. That is maybe an unstable situation where we could sort of immediately drift off into, we could very, very quick, you know, as soon as somebody taps the brake, traffic is going to slow down. So it's a typical assumption that's made, and I think that it's actually justified. And if we make that assumption, so if we assume that that the velocity actually depends on the density, then suddenly we have an honest-to-God differential equation. Okay. And what is this guy? So this is the conservation of cars equation, and it's a quasi-linear partial differential equation. It's quasi-linear because the coefficient of the first order, sorry, of the derivative in terms of x has terms, or is written in terms of rho. Quasi-linear PDE, quasi-linear homogeneous PDE, homogeneous first order. First order partial differential equation. Okay, so in particular, it's going to be a little tricky to solve. You can convince yourself pretty quickly that wave equation solutions aren't going to work except in very specific cases. but that's okay because now we've got the method of characteristics. All right, let's maybe take 5 if that works for everybody, and I will be, yeah, so let's take a quick 5-minute break. So it is 2:41 Boston time, and I will be back at 2:46. But in the meantime, let me know if you have any questions. Okay. I have to admit, mostly taking these breaks, I just have to get up and move a bit, like take a walk or something. It's just sitting for 3 hours is not super easy for me. That's correct. Yeah. So the bonus homework assignment can fill out your homework grade, but I'm not gonna spill over your homework grade into your final exam grade. Generally, I mean, there's some, I don't know. Yeah. Yeah. Thank you for checking that. Good question. Okay. So So here we go. So we've started off, so we've got this one-dimensional traffic flow, and it's based on density. And with fairly mild assumptions, we've actually come up with this differential equation, right? Like if we think about it, this differential equation is, we have the assumption that velocity is a function of, the velocity is a function of density. But otherwise, that, we're kind of okay with that, right? And there's otherwise basically we've only assumed that like cars don't spontaneously exist, pop into being or disappear. So this is a pretty general equation that we've written down. And so the only thing that we need to do now, and the assumption again that speed depends on density is again an intellectually satisfying equation because it means that it doesn't depend on position or time, which would be weird as well, right? It certainly might, if there's something like a speed limit change or a speed trap or something. But like when we do this kind of modeling, we often, at least as a first pass, want to make assumptions that should sort of hold for all time and space. And this is a good one. It's kind of the only thing we can do for that. Okay, but we still need to actually specify this relationship. We can look at some elementary traffic models, and we're really going to analyze one in today's lecture. But we can, of course, do this whole. We can, of course, do this whole thing for other traffic models or anything else we call it. Elementary traffic models. So in general, we probably want velocity to be a decreasing function of density. We want D to be a decreasing function of rho. So two simple examples. So one, and this is the one that we're going to follow through today, is just, well, okay, if we want to be a decreasing function, what's the simplest thing we can do? There we go. And what does this represent? So if this is rho and this is v, then this represents the maximum velocity, right? When there's no traffic density at all, this is the maximum you're going to go. This is the speed limit, effectively. And this, of course, is going to then be the maximum traffic density before density actually grinds to a halt. Rho max. Another model that is used is one that fixes a sort of positivity requirement. So this is sort of a, kind of a negative exponential model where we have some asymptotic velocity. So here we sort of assume that density can actually become infinite, which is probably unrealistic, but it's with the assumption as well that sort of, even if you have, bumper to bumper traffic, it's still going to move at some sort of minimum velocity. So we're going to look at this one. And here the equation for this model is V of rho, V max, 1 minus rho. Okay. And so we can see, so when rho is equal to 0, it's v, so it's a linear function. When rho is equal to 0, it's v max. When rho is equal to 2 rho max, it's 0. Okay, so we're going to look at this guy. First, though, okay, so in this case, so then, just to fill this out, then C of rho, right, is going to be prime of rho is going to be the derivative with respect to rho of rho times v max 1 minus rho over rho max, right? So v max, sorry, rho times the velocity. And so in this case, C is just going to be v max 1. This is now going to be, so yeah, derivative of rho is 1, derivative of rho squared is 2 rho minus 2 rho over rho max. And so then we actually have like an honest to God quasi linear differential equation. You can just plug it, see what we get. All right. Okay. So let's use the method of characteristics. So before getting specific, I'm going to say something quite general. So the idea here, right, is that we want to solve find, in this case, it's going to be x, t. So functions of x and t such that specific. The DDS of rho of xt, which is of course going to be d rho dt. Oh, sorry, I'm actually doing the proper order. D rho dx dx ds. Plus partial rho partial t dt ds. In this case, again, it's homogeneous, so it's going to equal 0. So this gives a couple of equations. So first, this gives d rho ds equals 0. Great. So second, find such that this, sorry, let me write the right-hand side again. Hasty here, so that this is going to be equal to the equation that we derived. So partial rho partial t plus c of rho partial x equals 0. So this is going to give us 3 ODEs. Again, the whole one, d rho ds is equal to 0. We also have dx ds is going to be c of rho. And we have dt dtds is, well, 1. Yeah. Okay. So this first equation here, of course, is going to tell us that along the characteristics, rho is constant. And second, the fact that dTds is equal to 1, it just means that t is basically some linear shift in S. First, along the characteristics, rho is constant. Second, dTds, so t is equal to S plus possibly some t naught. But since that's just a shift and we don't really care about S, so we can actually rewrite these equations in terms of t. We'll just say, okay, well, let's just fix t naught equal to 0, and then we can rewrite the differential equations in terms of t. In particular, dx dt is equal to 0. Okay. But again, c rho is constant. The rho is constant. So c rho is constant. So that means that along this this characteristic, so x is just equal to c rho times t. Plus x naught. Okay, so again, what do we have? So again, we have some linear functions. We have linear characteristics. But unlike before, where we had linear characteristics of constant slope, right? If we go back up here, the characteristics all have constant slope, right? The slope was just the flow. This is no longer true, right? So down here, we've got linear characteristics, but the slope may vary along the boundary conditions. Okay, so any questions? So the picture here is if we have x and t, then as so let's say that we have over here like an initial condition of the form. So we have rho of x 0 equals something like p of x. So we have initial conditions, so some initial density for the function. Then what this is telling us is that the slope of the characteristics is actually given by slope of characteristics is given by rho. So in particular, the slope here, we would expect to be steeper than the slope here is going to start being less steep, and the slope here is going to be less steep and less steep. Okay, so any questions about that? That's what we're in for. And so we can think about then, just drawing this picture, actually, we can see exactly what's going to happen. So if we have some sort of initial condition like this, and the characteristics are constant along, and the value of rho is constant along the characteristics, then you can see that what's going to happen is by the time we're out here, sorry, this is going to start going down, having gone down a little bit, gone down quite a bit. We're going to kind of get this thing like spreading out over time, right? So if higher density traffic moves slower and lower density traffic moves faster, we're eventually going to get this kind of long tail that moves out faster and faster and faster over time. Okay, any questions? Okay, so again, this is quite general. So this, what I've said here doesn't actually depend on C. It doesn't depend on what we pick for our relationship between traffic density and velocity. It turns out that very, very interesting things wind up happening with this set of equations. And that in particular, we can sort of set up different initial conditions and watch what happens as they play out. And what we want to find is, we really want to find models for three things. We want to find models for acceleration. So for something like a stoplight turning from red to green, where we have initially a high density thing and then it flows out. Model stoplight turning green. Green, stoplight turning red. Turning red. And we're going to say slash traffic jam here. And what we really want to know is how fast these phenomena move. We really want to understand how these phenomena move. Right, so we really want to understand things like if we have a traffic jam, right? So if somebody slams on their brakes, how fast does that shock wave go back through the traffic? And the reason is that, of course, you can already see, so solving PDEs is hard, we know this. What we don't actually want to do something like try to set up, if you were thinking about like modeling like a city or something, or even like a road with like 3 stoplights on it, we could think about how to set up boundary conditions for that, and we could be very, very careful. But it's a lot easier if we can just figure out what this model is telling us about the general behaviors, and then piece those general, stick those general behaviors together like Legos, which we sort of know that we can do, since everything that we've done is conveniently local, right? Depends only on local phenomena. So if we really understand well how the local phenomena work, We don't have to actually go through and solve a PDE by hand. We can sort of think like, well, I know what happens when a stoplight turns green, and I know what happens when a stoplight turns red, and I can calculate how fast those phenomena move at each other. So that actually gives me a high-level model that I can then plug in, say, on an entire road network. And that then that actually has the strength of the theoretical robustness of the differential equations, plus sort of much more practical computability. It's sort of fun, you know, you get to think about complicated systems and snap together these complicated solutions. And that's a much more efficient way of solving these problems than trying to write down some hideous, like hideously complicated boundary solution. Sorry, boundary condition and then solve. Okay. So first things first, some weird stuff is going to happen. So example. I want to call this example non-smooth solutions, maybe. Okay, so this is we're going to start getting into things that can go wrong with PDEs. You could teach an entire class, like an entire semester long class called Things That Go Wrong with PDEs. But basically, from a certain perspective, these are either pathologies or interesting features. And one of the interesting features of things like quasi-linear PDEs is that you can get non-smooth solutions. So let's look about this. So let's look at some of this kind of like non-physical example. So look at the non-physical example where V of rho is like the simplest thing that we could imagine it is. It's just rho. So this, of course, isn't physical because if we were thinking about a traffic flow analogy, this would be a situation where the denser the traffic was, the faster the cars went. Which, I mean, insert your own joke about whatever city you feel that's true about here. So in particular, C of rho is going to be the derivative, which is d rho of rho squared, which is just 2 rho. Great. Okay. So the equation is now going to be rho of t plus 2 rho times the partial derivative of rho with respect to x. And okay, let's solve, maybe I should say. Let's solve this equation with the boundary condition that the initial configuration is going to be given by this discontinuous system. So we've got 3 when x is less than 0, and we've got that x equals 4 when x is greater than 0, right? So the picture here is like rho of x0 is this. So we've got some lower density thing to the left of 0. We've got some higher density thing to the right of 0. Again, this is a non-physical situation where cars speed up the denser the density of traffic gets. So I'm not going to maybe spin out the analogy, but let's just see what happens. All right. So yeah. So quick question. Which part do we expect the cars to move fast? Sorry, the cars to move faster on. Do we expect the cars to move faster over here or over here? A or B? What do we think? Based on our model and our equations, are the cars going to move faster in A, where the density is 3, or in B, where the density is 4? Again, in this pathological model. Any ideas? Any guesses? It's a 50-50 chance, right? You could flip a coin. So in A, so again, I think that, so you guys are completely correct if you think about an actual model. Because in an actual physical model, of course, the lower density, the traffic is going to move faster. In this pathological model, what I've specified that V is equal to the density. So in fact, the cars will be moving faster in B because the density is higher. Again, it's pathological. You would be absolutely correct if this was a model that reflected the physical world in any way. Here, V is equal to rho. B is faster. And so what that means is that when we kind of think about it, we're going to get this case where the block of cars at B, the higher density block, is actually going to be speeding away from the lower. Why? So this is why is V equal to rho? So just to check, is your question why is V equal to rho, or given that V is equal to rho? Well, so so in this case, given that I've specified, I've just said that the velocity is going to be equal to the density. And so given that the velocity is equal to the density, and given that the density is greater in B, the velocity will be greater in B, right? In fact, yeah, so in fact, V of x 0 is going to be as well 3, 4. Yeah, it's a little bit of a cheat, because again, this is like we've been talking about like very sort of careful physical examples, and all of a sudden I've like gone completely off script, not off script, but I've gone completely like off into the deep end, and I'm talking about this really pathological example. And I just want to do it because it's going to show you an interesting piece of behavior, and then we'll dovetail back to the normal physical models. But yeah. Any other questions though? Thank you for asking. It's good. It's good to get everything solidified here. Okay, so something fun is going to happen now. So basically, we know that this guy is going to zoom off. So what's going to happen? actually have my axis in the middle here. X and t. So we know that the high density thing is going to zoom off much faster than the lower density portion. And we know that the characteristics, right? So the characteristics are just going to be given by, our characteristic equation that we derived. So x is equal to c rho t plus x naught. So this is going to be, the characteristics are x equals c of rho t plus x naught, which is going to be either 3t plus x naught or 4t plus x naught, depending on what x naught is, right? So for x naught greater than 0, for x naught less than 0. So we're kind of going to get something that looks like this. Where this is x equals 3t plus x naught, and here we've got x equals 4t plus x naught, and then of course the density is going to just be, the density is going to be 4 over here, rho equals 4, and here rho equals 3. So what happens in the middle? What happens in R? It's like suddenly we have our solution space. Suddenly we have the xt plane split up into 2 different sections, right? We completely understand the behavior, sorry, to 3 different sections. We completely understand the behavior in section 1. We completely understand the behavior in section 2. But there's this region in between that we can't push, we don't seem to be able to push forward the boundary conditions from. Okay, so, but we can still use the method of characteristics. And this is kind of how. So if we make the assumption that, so in region R, so I should say, R is of course going to be where, oh, did I, sorry. This should be 2 rho, I apologize. It should be 6 and 8. So this is where, this is where 6t is less than x is less than 8t. So it should be 2 rho, because that was we're looking at the derivative of rho times v. So so if we assume the characteristics are linear and pass through 0, what happens here? The characters are linear, which they have to be because those are our characters, and pass through 0. Pass through the origin. Then we must have that x equals 2 rho times t. So for three less than rho less than 4, we can solve this then. For rho is going to be equal to x over 2t. And so in particular, this is going to be a linear function So for fixed t, so it's going to be a linear function interpolating between rho equals 3 and rho equals 4. So let's say, so at for example, so at t equals 1, for example, what we're going to get, we're going to get, so if this is x and this is rho, so the density 3 region will have moved up to 6. Right, so this is 6. Here's our density 3 region. Our density 4 region will have moved up to, so the velocity of that is 8, so the density 4 region will have moved up to 8. This is, of course, not to scale. And what do we get in between? We get the function, so for t equals 1, we're going to get x over 2 interpolating from 6 to 8. So and indeed, this will go from 3 to 4. And picture, this is what's called a fan. So as before, we're going to have our region 3 and our region 4, and in between, let me do these in a different color, actually. We have a fan of solutions. And then what we're seeing here is exactly, so this is, say, at t equals 1, exactly corresponding to what we have above. Okay, any questions? So this is one kind of thing that we can get. Another kind of thing that we can get, and in the interest of time, is a shockwave. So a fan is the kind of situation where you have some interpolation between two solutions. That's like a, given, so the interpolation will be dependent actually on the geometry of the characteristics. So since the geometry of the characteristics here is linear, it's a nice sort of linear interpolation. But if we had some sort of more interesting characteristics, then the interpolation would also be possibly more interesting. But in particular, it's discontinuous, right? So this is a sorry, it's not discontinuous. Sorry, it's not smooth, right? It's not differentiable along these boundary lines, which is very weird for a PDE, right? For a partial differential equation, what's happening. And of course, what's happening is it's reflecting a lack of differentiability in the initial condition. Any questions? Okay, so let's look at another example, the example of shock waves. So what if we swap the initial conditions? So now rho of x0 is going to be 4, 3. Okay, so we draw the picture again. So x rho. Now we've got 4 over here, we've got 3 over here, and now we've got this weird situation where the cars in 4 are supposed to be moving faster than the cars in 3, right? Cars here move fast, and the cars here move slow. So what can possibly happen, right? How can we have this this huge density of cars overtaking another group of cars? It's not. Well, the solution kind of, just in interest of time, I'm just going to state it. So the solution is, of course, that, you know, again, we should think of this density is not individual cars, right? Individual cars are sort of moving along so faster, faster, faster than they hit and slow down. But what has to happen, right, is that this, so this picture must move forward, right? In order to satisfy conservation of cars, if we've got more cars coming into the system, it must be that this discontinuity moves forward, right? Since the discontinuity is overtaking the other thing. Discontinuity must. And this discontinuity is called a shock. Or a shock wave. And it is, you know, for exactly the reasons that we think about, you know, what is a shock wave? It's when you get, I mean, almost a discontinuity in high pressure systems, in gases and whatnot. So the interesting thing about this system, so the interesting question is how fast does the shock wave move? And we can kind of try to answer that. So again, you know, the picture that we're going to get here, right, is that if we've got high density stuff down here, right, and we've got lower density stuff here, then we would expect steeper characteristics to the left-hand side and less steep characteristics to the right-hand side. So here, this is going to be x equals 8t plus x naught, and here we're going to have x equals 6t plus x naught. And so we have this sort of discontinuity along here. That's going to be where our shock wave hits. Or something is going, or sorry, something is going to have happen along here. I think actually what happens is we split the difference. Okay, so how are we going to determine this? Okay, so clearly our solutions aren't smooth anymore. Our solutions aren't even going to be continuous, but that's okay. There still exists a conservation equation. Okay, so solutions not continuous, but the conservation equation is going to tell us something. Conservation still holds. So in particular, what that means is that if we've got our shock wave, right, moving along, and we think about a little bit to the left of our shock wave, right? Think about what is the flow of cars through a little bit to the left. And the flow of cars a little bit to the right. So what's that going to be? Okay, we know what that, so that's going to be Q minus and Q plus. We have to have, so it's got to be the case. So here, sorry, Q minus is going to be Q at Q just a little bit to the left. So here this is, so if this is X minus and this is X plus, so Q minus is going to be the flow a little bit to the left at time T. Q plus is going to be the flow a little bit to the right at time T. So the flows might be different, but the total number of cars exiting Q minus and entering Q plus has to be the same, right? That's conservation of cars. We can't just create or destroy cars. So in particular, it's got to be the case that Q minus, which, well, what is Q minus? Okay, so it's the density times the velocity, right? It's the flow. So the density a little bit to the left, its velocity a little bit to the left, has got to be equal to the density a little bit to the right times the velocity a little bit to the right. Sorry, I think I said something correct. The flows have to be the same. The number of cars crossing these boundaries has to be the same. Okay. We want to use this. To determine the speed of the shock wave. We'll call this dxs dt. Where actually does our shock wave sit? Okay. So what is this equation going to give us? Well, our velocity is going to be, so if we think about the shock wave as being fixed and we think about a relative velocity between them, this is going to be prime of t times a relative velocity. Dxs. So the relative velocity between the cars and the shock wave, that's got to be equal. Sorry, there should be a plus there. T. And so we can solve this. Dxs dt is equal to, I'm just going to state the solution, rho minus v minus rho plus v plus, or rho plus rho minus. Okay. So this is great. So the this is actually a really general formula, right? Remember, I started talking about this in the context of this problem, but this formula that we've derived actually is derived in terms of this formula that's derived is actually we've actually derived it in generality. Sorry, this is delta Q over delta rho. Yeah, we can call it that anyway. I think technically we probably want this to be minus. All right. So then in our example, what do we have? Well, we had that Q was equal to rho squared. So delta Q minus delta Q is going to be minus delta rho squared. And what do we have? So on the left side, sorry, I'm being a little doubtful here. Are we gonna have that? Yeah, no, okay. So we should have anyway, so rho minus equals 4 and rho plus equals 3. So dxs dt is going to be where I'm a little. I think that this, sorry. The one thing I quoted instead of working out, I think is incorrect. I think that that is where we should, is actually what we should get. Because certainly we expect this to be moving in a positive direction. So anyway, so what are we going to get? So this is rho squared, and so we're going to get, sorry, 3 squared minus 4 squared over 3 minus 4, or 7. And so in the picture, this then justifies the picture that I drew before, where we have this moving forward, sort of halfway in between the speeds of the other two. Okay, so we have a quite general formula for the shock waves. We now understand, so we understand now what happens in the case of the, so we understand what happens in the case of the fan. So when we have two systems moving apart, we get a linear interpolation between the two when our function's linear. When we have two systems moving towards each other, we're going to get a shock wave, a linear shock wave. Before we jump on and I finish up by showing the actual non-trivial model, are there any questions? Okay, so let's actually apply this to the traffic model. So here, if we recall, what did we have? We had rho of t plus v max 1 minus 2 rho over rho max times rho of x equals 0. The picture here, of course, was so our velocity versus density now is something that makes sense. So v max and rho max. So if we look at a red light turning green, the boundary condition there is going to be that we have like maximum density to the left of the red light and 0 density to the right. So boundary condition. Rho of x0 is going to be rho max for x less than 0 and 0 for x greater than 0. So characteristics are going to be given by x equals c rho t plus x naught, which in this case is going to be v max 1 minus 2 rho over rho max times t plus x naught. And so we know what this picture looks like at this point. This is going to be, so when rho is equal to 0, this is going to it's going to be v max. Over here, this is x equals v max. And on the right-hand side, when rho equals rho max, this 2 actually means that we're going to flip the sign. So this is x equals minus v max. And we get something kind of interesting, right? And then, of course, we're going to get a fan interpolating between. So the solution actually is going to look like a sort of tilted solution moving away from the center. Draw it over here. I've got plenty of space. So if we have x and rho, it's actually going to look like this. So where this is rho max. And this sort of makes sense, right? This is really exactly what we would expect. It's you know, we have some cars zooming off ahead. Only the cars that are at the front can do that. Or so even if everyone's moving, the density. So yeah, so we get in this interesting situation where everyone can be moving, but the density wave diminishes backwards away symmetrically from the light. And this is something that one could go test, but at the very least, it gives us something that if we want to plug into a more sort of complicated, interesting model, this is behavior that we could add in by hand without any trouble, right? Now that we have the solution, you can just think about having like a long linear model with the road. We now know exactly what happens when we have when we run forward a discontinuous density change. So the thing we get is waves going outwards in both. We get a sort of a wave front moving outwards in both directions. The other way, so the stopped light in the traffic jam. So we have a green light turning red. Well, what's going to happen here? Well, again, what's going to happen is it's going to be roughly the same thing as we derived because we're in a linear situation. So the only thing that we need to figure out here is what the initial boundary conditions are. So now, the boundary conditions are going to be roughly that we're running into a traffic stop, right? So rho of x0, in some sense, you know, it's a brick wall. So we'll just say that it's a high density. So it's going to be 0. We could of course pick something that wasn't 0, but 0 for x less than 0, rho max for x greater than 0. And then we can use our equation from before. So we had ds dt, sorry, dx. S dt is equal to delta q delta rho. And so if we have, so if we have a shock wave, so in this situation, our shock wave is going to move backwards. Our shock wave moves dx dt it's q of rho max minus q of rho naught. Max minus rho naught. And we know what this picture is going to be, so we actually have sorry. So we actually have that this is going to be stopped here. And then we've got characteristics moving forward. Oh, sorry, this is not quote, sorry. This is in the linear case. Nonlinear case where we're going to get something that looks like, sorry. This is in the linear non-affine case. Get a shock wave moving backwards. Here. Okay, so basically, sorry, I'm rushing a little bit because I want to show you one last thing. So in the last kind of, so the great advantage of this, of course, is, as I said, at the beginning, we can use this differential equation modeling to model sort of specific components of situations. And then as a final step, just sort of stick them together like Legos if we do it carefully, right? If we feed the sort of the situation from one to the other and we're careful about it, this allows us to model like really complicated situations in terms of little component pieces. And we've seen a lot of examples of that already, like, with the SIR models, when we start looking at multiple cities and things like that, we can understand the local dynamics and then solve things out explicitly and then use that to piece together this bigger, more complicated picture. And that's really like what mathematical modeling is about. There's this, the reason that we do all this idealization and the reason that we do all this kind of like careful reasoning about these really simple cases is because we don't want to stop there, actually. We actually do want to push things forward to the really kind of complicated cases that we're dealing with. It's just that the best way to do that is to deeply, deeply understand the very, very simplest elements. And, it's a fun field to be in because, you get to do a lot of stuff. You get to do mathematics, you get to do simulation, you get to do computer science, you can sort of pull all of these pieces in. And the interplay is always there between, so the interplay within, the mathematics of using, trying to use the mathematics to say precise and careful things that we can really deeply prove about the models. And then using these higher level heuristic techniques, whether that's things like phase diagrams or numerical solvers or, other kinds of simulations you can run. There's all kinds of beautiful simulations coming out now of sort of stochastic probabilistic things where you drop agents into systems and see how they would make their way through them. It's a pretty, at the end of the day, though, there is always this interplay between that kind of modeling and what you can prove by hand. Because at the end of the day, you can do a lot of you can show a lot of models and they're great, but if you want to prove something, it really helps to have a handle on what the fundamental little pieces are. And for just one last little example of that, last example. So here's one picture that we have of traffic. We could have had another picture of traffic, a more agent-based model. So the idea here would be that we could actually try to model every car as a differential equation. Model each car. So like a simple way to do that might be, dxi dt. So what is the position if we have n cars, the car in position xi? Let's say that it's going to depend on, so the rate of change, so how fast it's going is going to be some maximum velocity times the distance between it and the car in front of it. Normalized out as a hill function. Wow. Okay, so in principle, this is just some big nonlinear system of ODEs, right? And what that means, so this is a very, very simple rule, right? So V is the maximum velocity, A is roughly, so we think like when the cars are sort of, they're pretty far apart. So when the difference between them is small, this becomes linear, and so it falls off very fast. When the distance between them is large, then it basically goes to the maximum velocity. So we can posit some simple rules, and then we can actually go over and see what happens. Produce a little model here. And so, here's an example of our non-physical traffic model. So this is again, you can start. So warning with characteristic models, if you do things in a sort of silly way, you can start with boundary conditions and then try to push things out in such a way that that you actually don't get a function. But so this is the idea. So we have a bunch of little cars, right? And we have one say go forward and stop and then go forward again. And we want to see if that propagates backwards. Okay, so here we can see that stopping, and I just made a little animation, and here we go. And we see this little traffic jam, right? And we can actually see all the dynamics that we just saw before, where we have the little traffic jam, it propagates backwards. And and in this case, the traffic jam actually, sorry, it doesn't propagate backwards. Actually, it moves forwards since nobody ever actually stops, right? If it stopped, we could imagine it propagating backwards. But here, it moves forwards as the thing pauses, and actually we can see the jam move. And so then there's an interesting question. So this is an agent-based model. We've been talking about continuous PDEs. Is this agent-based model an example that could come out of basically sending little agents through the equations for a PDE? And that is another area, which is, again, if we had 2 more weeks, what I'd really like to do is talk about that back and forth. So we've talked a lot about atomization, we've used it to write down equations, but there's also a really fun game that you can play, or sort of a beautiful set of mathematics that goes between going backwards. So starting off with PDEs and trying to use them to extract the sort of behavior of individual elements of the system. So that is, that's what I got for you. It's been, so that's what I got for you guys. It's been fun having you sort of in class or out and around. I'm really looking forward to your final projects. I'll get you guys feedback on your drafts later this afternoon or this evening. And yeah, I hope that you've had a good time. I want to really commend everyone for putting up with I mean, three-hour-long lectures twice a week is no joke, especially those of you that are in Beijing, or sorry, that are in China or in India, where you're watching this at 12 o'clock at night, 1 o'clock in the morning right now. So thank you guys very much for all of your patience, and I hope to see as many of you in the fall as I can. And for those of you that can't make it this fall, I hope to see you in the spring. So please let me know if you have any questions about advising, about Northeastern, about anything that's going on with your personal sort of journey to get here. I know people are going to start arriving pretty soon. There will be an orientation again on the 3rd, and that will be through NU Flex, I hope. It will, whatever it will be both online and on ground. But I'm hoping that will be like entirely through NU Flex, so that everyone can kind of get some practice with that. So if you are going to be in Boston for that, we'll be sending out an email here in a day, well, later today, hopefully. And just please let us know, and it'll be great to meet you all in person. And yeah, I hope that you've had fun, and I'll see you all soon. I'll see some of you in machine learning, I hope.
Professor?
Yeah.
So when I looked through the orientation schedule, I saw there's like something like a sample lecture about stats.
Yes.
Could you please explain, or I just want to get more information about it.
Yeah, definitely. So yeah, sorry, I'll be sending out something a little more solidified here pretty soon. But basically, what the orientation is it's an opportunity to introduce you to myself, to Chris King, who is really the architect of this program. He also teaches probability 1 and 2, and is definitely, you should just look at what he researches. I mean, he's in the kind of quantum computing, quantum cryptography, everything in that world. So introduce you to myself, to Chris, to Egon Schulte, the head of the department, to Patricia Corrigan, our co-op coordinator, and hopefully to Adam, Owana, Stuart, and the other folks that teach in the program. We'll see who can make it in, but it'll basically be a quick introduction. And then for those of you who are interested, we'll be doing a little kind of statistics boot camp. Just honestly, it's mostly about getting people like in a classroom to interact with each other. So since you guys have done this, you'll already have a little bit of it. But the other thing is basically to just like define some statistical terms, because like this is becoming less common, but like, you know, I managed to go through my entire undergrad without ever taking a stats course. And there's just some like simple things like, you know, what is a confidence interval? How do we do a Monte Carlo simulation? Like, what are these, like, you know, what are these, you know, what, you know, how do we bootstrap a confidence interval? Like, what are these terms? Like, what do they mean? And how do we use something like Python or R to do some of these computations? So it'll be pretty short, it'll be pretty light. It's not going to be graded or anything, but if you want a refresher on some of those concepts, if you want to see how to implement them in R, if you want to hang out and solve a problem or two and just meet some people, then I would highly recommend that you show up. And you should certainly show up to meet for the first part, where you'll be talking to, well, myself and you know, less importantly me, because you guys all know me, but Patricia, Egon, Chris, and hopefully Adam.
Okay, thank you so much.
Yeah, definitely. Any other questions? All right, well, I'll be sending out a sign-up sheet. Absolutely, I'll be sending out a sign-up sheet for the presentations the next couple of days. And I want to thank you guys also for putting up with the fact that I've been traveling, and so this has been kind of crazy. So I'll be flying home tomorrow and then quarantining for a couple of weeks. So after tomorrow, I will have like all the time in the world. I've been in and out of various quarantines. But if I don't get it out today, I'll get the sign-up sheet out by Thursday, and that will be for signing up for presentations on Monday. So, all right, thank you all, and I've got a meeting after this directly. So Anna, I'm going to throw you a link to a different meeting, but there you go. And I'll meet you over there in just a minute. Absolutely. I mean, I'll see you all on Monday.